what you can see on the screen, there's a picture of three of the world's most famous mathematicians. All right? Kurt Gödel, Albert Einstein, and I'm not sure who that guy on the end is. But I hope to, you can see, it's amazing what Photoshop can do. Okay? So, but to begin with, as we're going to talk about this, I've got a problem for you. I want you all to work on this. You are chess players. It is white's move, and does white take the rook? And I would like you to work in groups of two. Well, you're also spread out, but this is such a disparate group. But, okay, figure out, does white take the rook? Okay, I want to show you where I got the ideas for this talk. Early in my career, I read this book by Nancy Pearcey and Charles Thaxton called The Soul of Science. And this helped me understand a lot about the philosophy of mathematics and some about the problem we're going to talk about. And I want to be a good academician and tell you my sources. So this is one of them. Another one is by Stephen Barr called Modern Physics and Ancient Faith. And he talks about 5 different revolutions in modern physics that make it more likely that Christianity is true, or that give evidence for the truth of Christianity. And he's the one who put me onto this about how Kurt Gödel's discovery actually helps to prove that Christianity is true. Another one is Morris Klein, The Loss of Certainty. This is a book, Mathematics, The Loss of Certainty. It's a lot like Eugene Wigner's talk called The Surprising Effectiveness of Mathematics in the Physical Sciences. And you remember there's a talk, I think he gave in 55, in which he says there is no reason that we can know of that mathematics, we cannot prove that mathematics is true, and we really don't know why mathematics works. He says, but it's a wonderful thing, and it's a gift, and we should be thankful for it. That's the conclusion that he comes to. And then finally, of course, and this is where I got the picture of Gödel and Einstein, and this is a book about their friendship. This is when they were both at the Institute for Advanced Study in Princeton, and I don't know why they're wearing hats, but several of the mathematicians in this talk will have hats. So it's basically a talk about hats and what goes on under them. So that's what this is about. Now this book taught me a little bit about Gödel and the incompleteness theorem. But the interesting thing about this book shows us how Kurt Gödel proved that in any universe where relativistic science is valid, that time has no meaning. Now, there's a book in our library recently that talks about the next revolution in physics, which is the elimination of time. And I tried to read that book. I didn't understand much of it. And in this one, he tells about the mathematics of it, and apparently people think that Gödel's reasoning is true, but nobody knows what that means. You know, a world without time, any Einsteinian universe is a world without time. Well, nobody has really been able to figure out how that works or what that means. That's not what I'm going to talk about, but that's what this book is about. So if you're interested in that, go to this book. Okay, but I want to talk with you about a little bit about the history of mathematics to set up what Kurt Gödel did. And so this is, especially if you're a mathematician, you'll know all this, but I just want to remind you of this. And that it really starts with Pythagoras. And when Pythagoras says all is number, he did not mean that the whole universe can be described by numbers. He literally meant that the only real thing in the universe is numbers. And that everything that we perceive is just, we perceive an aspect of numbers, and that numbers are the only real thing. And of course, you know, the Pythagoreans then said that everything in the universe is number, and that everything in the universe can be described by the relationship of number. By number, he meant what we call, the natural numbers, the counting numbers. Now, of course, this view was falsified by a man named Hippasus, who proved that the square root of 2 was irrational and could not be proven or could not be described by the relationship of any 2 natural numbers. And the story is that the Pythagoreans were so upset about this, he discovered this, or he made it known to other Pythagoreans while he was on a boat, probably on the Mediterranean or someplace, and they were so upset with him that they drowned him rather than to accept his findings. The next step would be Euclid, and of course Euclid is the father of geometry. But the thing that I want to remind us about Euclid is the one who introduces the concept of certainty into mathematics. Now, some things are true, but they're contingently true. For instance, it's contingently true that I'm Chuck White and that I'm speaking in English. Now, someone else could be giving this talk, and someone else could be speaking in French or Swahili or some other language. Those things, that I am who I am and my language is English, those are true, but contingently true. Euclid showed us how we can prove that some things are certainly true and that they could not be otherwise. For instance, that the angles from the inside of the interior angles of any triangle add up to 180 degrees. That could not be any other way. That's certain. And the concept of proof and of certainty come to us from Euclid. Okay, now nobody knows what John the Apostle looked like. So I'm pretending that this is John the Apostle. And probably because he's got a bound codex there, that's probably not what John looked like, or at least it's an anachronism that he would have a book of that sort. But John, of course, said, "Enarche ein ho logos," that in the beginning there was logic, or in the beginning was the Word. And of course, logos means word or reason or mind, or not so much mind, but an idea that's expressed. And so when John is describing the Son of God who becomes incarnate, and that he was God and was with God, and he calls them the Logos, he's expressing the idea that God, or that rationality is part of God's character, and that God instantiates rationality and logic. And so there it is, that's another way of translating it. Now, Galileo came along in that same tradition about 1,400 years later. And the wonderful thing that he said is that mathematics is the language in which God has written the universe. That we can use mathematics to describe the created world. And that is a wonderful gift. And so that our minds which can deal with mathematics and our minds which can understand the world can be trusted. And then, of course, probably here's the culmination. Who is this man? Isaac Newton, right. And of course, the apocryphal story is that Newton figured out that the same force that made the apple fall actually makes what happen? Makes the moon go around the earth. Now, I can remember when I was a physics student figuring out how the moon stays in orbit. And to figure out that orbital velocity is 17,600 miles an hour. And that because of the distance of the moon, that the distance that the moon moves in 1 hour is also the same that it falls. The horizontal distance that it moves and the vertical distance that it moves are the same, so that in its orbit it is just continually falling around the world. I mean, I didn't know that before, and I can remember as a physics student just how exciting that was to me to figure that out and to learn that. I also remember one time I was doing physics at this time. I was 16 years old, and I had just got my driver's license, and I was driving around, and I happened to see an airplane in the sky. And for some reason, and this was not like what happens in The Gods Must Be Crazy, but in the movie The Gods Must Be Crazy, somebody throws a Coke bottle out of an airplane. Well, what happened in my experience is there was something on the airplane, under the airplane, that fell. And so as I watched it, I saw the airplane, and the airplane flew like this, and what started to fall fell right under the airplane. And like when you're a kid and you throw something out the car window, it goes back. But physics says, no, it shouldn't go back, it goes straight under. And it was like God was showing me that physics is right by putting me in that experience where the object fell out of the airplane and landed right under the airplane, just like physics said it would. Well, Newton is the one who explained all that. And it was such an exciting idea for humanity that there was such a thing as natural law, and that they could be mathematically described, and that you can predict what's going to happen in the universe and understand it, that an English poet named Alexander Pope was so excited about it that he said this: nature and nature's law lay hid in night. God said, read with me, what's it say? Let Newton be, and all was light. It's like we never understood the world until Newton came along and gave us the mathematical language. Now, Galileo had said there was the language, but Newton actually told us what the words were in that language and helped us understand it. So if you put all these ideas together, beginning with Pythagoras and ending up at Newton, you get this consensus that we can use math. Oh, and I realize if you're British, you say maths, plural. But we can use math to understand the world because God built the Logos into both the world and our brains. That God, who is the Logos, as He created the world, created it according to the Logos, and that's as our minds participate in the Logos, we can understand the world God made. And so that, by the 17th century, that was the achievement of mathematics. It's all wonderful and good and happy until this man comes along. Anybody know who he is? Once again, it's a talk about hats. Look at that turban that he's got on. But what went on under that hat? Anybody know who that is? He's David Hume. Okay? And David Hume's great discovery was this: there are no elephants in Britain. Now, you should be shaking your head and saying, what are you talking about, Chuck? Now, David Hume never really said there are no elephants in Britain, but I'm going to tell you probably the dumbest joke you have ever heard. Okay? And the punchline is, there are no elephants in Britain. Okay? So, here's how the story goes. There are two men, and they are riding on a train from London up to Edinburgh. And as they ride on the train, they are sitting next to each other. One is here, and here's an empty window. And the man who's on the aisle is reading a book. And as he reads the book, he rips out a page. Every time he finishes the page, he rips it out, crumples it up, and throws it out the window. And so then he reads the next page, and he does it. And after a few minutes, this man says, "Sir, I notice you're ripping the pages of the book and throwing them out the window. Would you mind telling me why you're doing that?" And this man says, "Well, of course, I'm very happy to tell you. I'm doing it to keep the elephants off the tracks. See, if the train were to have a collision with an elephant, it would kill a member of an endangered species, create a lot of property damage, perhaps kill some human beings. So it's very important that the train not run into an elephant." And this guy says, "Sir, there are no elephants in Britain." And this man says, "Effective, isn't it?" Okay, now, if you understood that joke, find somebody else and explain it to him. And if you didn't understand it, find somebody else and have him explain it to you. So I want you to talk with each other. And I realize you're scattered throughout the room, but I would like you to, in groups of two, to make sure everybody understands it. Talk to one another and make sure you get it. Okay? Please do that. Turn around, talk to one another. Introduce yourselves in groups of 2 or 3. Okay, does everybody at least have an inkling as to where we're going with this? Does somebody want to explain to me what kind of a mistake is it? It's a logical mistake. Yeah, you're right. Okay, the man who is sitting here, they both agree there are no elephants on the tracks. Okay? There are no elephants on the tracks. Well then what does this man who is throwing the paper, what does he think causes there to be no elephants on the tracks? His throwing the paper. What does this man think the cause of no elephants on the tracks is? That there aren't any elephants in Britain, that elephants don't walk around loose in Britain. So he's made a mistake about cause and effect. This man thinks the cause of no accidents with elephants is throwing paper. This man knows that the cause of no accidents with elephants is that there are no elephants. Okay, what is that proving? What is that or not proving? It's illustrating. It's illustrating the idea that David Hume questioned whether cause and effect could be proved. And as a matter of fact, he asserted cause and effect can never be proved. He said you can prove that A always succeeds B, but you can't prove that A causes B. And just because post hoc propter hoc, which means after this because of this, and that's not true. Just because two events happen in succession does not mean there's any causal relationship between them whatsoever. Now, David Hume also proved, and I'll just throw this in for extra credit, that you can't know that the objective world exists. You can't prove that you are not having a dream. You can't prove that you're here. All you know is what goes on inside your mind. You can't know you can't know that you're not having a bad LSD trip. When I was an undergraduate, I went to Harvard University in the United States. And one of my friends, and there were a lot of very smart people at Harvard University, and some people were so smart that they found the classes at Harvard boring. And so what they did to make their lives more entertaining is they took LSD. And one of my friends got some bad LSD, and he took it, and he had a bad trip. And he lived in the room right below me. I lived on the 4th floor. He lived on the 3rd floor. And he had a braided rug in his room, a big circular rug. And because of the bad LSD he took, he thought that the rug was a whirlpool and would suck him down into it. And he was so afraid of that he cried out to his roommate and he said, "Stop me from being sucked down." Now, his roommate knew he was having a bad trip, but his roommate thought if he thinks he gets sucked down, he may go so completely crazy we'll never get him back. So my friend sat on the couch and held his friend having the bad trip on his lap with his arms around him for 3 hours so that he wouldn't think he was being sucked down. There's an example of what was going on in his mind was not what was happening in the objective world. And David Hume proved that there is no way, just given your mind, to prove what's going on in the objective world. And the other thing he proved, or that he showed, is that you can't prove that just because the sun came up today that it's going to come up tomorrow. You cannot prove the continuity of nature. So David Hume questioned and showed that there's no way to prove cause and effect. There is no way to prove the existence of the objective world, and there's no way to prove the continuity of nature. And since his time, no philosopher has ever been able to show that he was wrong about this. Well, the next step is, since we cannot prove cause and effect, there are no laws of nature. See, Newton had said there are laws of nature and they can be described by mathematics. But Hume cut the ground out from under that by showing that you can't prove cause and effect. Now, the laws of nature depend on cause and effect. Well, if there's no cause and effect, there's no laws of nature. If if the laws of nature are held up by the concept of cause and effect, you remove cause and effect, then you lose the idea of the laws of nature. And so non-existent laws cannot be described by mathematics. So that's a major blow to the Christian synthesis of how we think about math and how we think about the world and how we think about rationality. Okay, well, then comes this man, Immanuel Kant. And, okay, it went too far. And Immanuel Kant said, he looked at the idea of the objective world. And he said, David Hume is right. We can never experience or know the noumena, which is his word for the things in themselves in the physical world. All we can know is phenomena, which is what he called our thoughts. It's like if you want to go down, if you want to see the Titanic is sunk in like 3 miles of water. Now, you can get in a submarine and you can go down to the Titanic and you can shine a light on it and watch it through a television screen. You might even be able to watch it through, really thick glass. But you can't go to where you can't get outside the submarine because the pressure of the water will kill you. Now, you can use an electric arm and move things around on the Titanic, but you can never experience the Titanic directly. It's always mediated. In the same way, Kant said we can never experience the noumena, the things in themselves. All we can experience is the phenomena, which is what's in our brain. And so the real world is mediated through our brains. And so he said the mind organizes the phenomena according to 12 concepts, which are built into our minds like firmware in a computer. So remember what firmware is. The hardware is the computer itself. The software is the program. The firmware is software that's built into the hardware so that when you turn on the computer, the electricity, the first thing it does, it says, go find the operating system. Now that's firmware. It's an instruction for what the computer will do, but it's built right into the computer. Well, our minds are like that. They're organized in certain ways. And cause and effect, up and down, front and back, before and after, that kind of thing. Those are all some of the concepts that Hume says, that Kant says are built into our minds. And he argues that mathematics is one of the ways our mind uses to organize the phenomena. Because we wouldn't be able to think if we didn't have those organizing principles. But they're firmware built into our mind. They're not really there in the natural world, but they're in our heads. Okay? And so what people have said is Kant saved math in our brains by taking it out of the world. So math is something that works in our brains, yes, but it doesn't work in the world, or you can't prove that it works in the world. It works in the phenomena, but not in the noumena. Okay, so now we're taking another step away from the realistic kind of Scottish common sense realism that that culminates in Newton, but it's attacked by Hume, and then Kant tries to save it, but saves it in our brains by taking it out of the world. This is probably mathematical elegance. I don't know if there's a definition for mathematical elegance, but this is it. He's the one who said, well, if you take 1 and 100, it adds up to 101. And if you take 2 and 99, it adds up to 101. If you take 3 and 98, it adds up to 101. How many pairs do you have? You have 50, so it all adds up to 50-50. And the teacher probably was even more irritated at the end of that than at the beginning. But that is cool. And that's, every time I see a problem, I think, is there a Carl Friedrich Gauss way to solve this problem? Okay, but that's not why I'm telling you about him. What I do want to tell you about him is he wanted to solve the problem, how does mathematics relate to the real world? Does mathematics, is it just in our heads, like Kant says, or does it really relate to the real world? And so what he did, he said, well, I'm going to do an experiment. And my experiment was, what he wanted to do is that he measured the angles formed by 3 mountain peaks. to see if with that triangle it added up to 180 degrees. Now, to do that, he had to climb the mountains. He also had to invent instruments that were so fine that you could measure exactly where something was, within a foot or two at a several miles distance. And so he went through the whole thing, and he discovered that the instruments that he had weren't accurate enough. So he couldn't do it. Now, what we know from a sphere, let's say it had perfect instruments. What would he have discovered from his mountains? Yeah. Because of the curvature of the Earth, yeah. It would have been different. So it would have been less than 180 degrees.
Or unless you've got 3 points on a plane.
Yeah.
It would be a tilted plane and still.
That's a good point. Yeah. So I was just thinking from at the absolute peak. Yeah. Okay. Right. Yeah. But your point is well taken.
Wouldn't it have been larger than 180 degrees because it's a sphere and then it's larger than 180?
I thought a sphere would be smaller. I think with
concave, it's greater.
Depends on the curve.
Convex.
Well, yeah. When is it Lobachevskian? We're going to talk about that in a minute. So, okay. Well, now here's as people wondered about that, then they also started thinking, well, is math really true, even in our brains? And so people started wondering, is Euclid's fifth postulate true? Now, the first four are basically common sense, and everybody said that's true and obvious, intuitively obvious. Anybody ever use that phrase in math? It's intuitively obvious. I remember one of my friends was a math genius, and he was helping me with my math homework one day. And he helped me and showed me the answer, and I said, how do you know that's the right answer? And he looked at me and he said, it's intuitively obvious. Well, as a teacher, that doesn't help you at all, because he couldn't give me the intuition to say that. But anyhow, meanwhile, back at the ranch. Okay, Euclid's fifth postulate is that for any line and a point not on the line, there is one and only one line that's parallel to that first line. Now, is that true or not? And people wondered about that. And so this led to the development of non-Euclidean geometry. So where you have for a Euclidean plane, where it's flat, you have zero curvature. But if you have a surface of a sphere with positive curvature, it's going to be, as you said, greater than 180 and backwards from what I said. So I was wrong about that. You were right. It's greater than 180. But then if you have hyperbolic geometry, it's going to be less than 180. Yeah, depending on what kind of curvature. Well, this created a major problem for mathematicians. Because, how can you have different kinds of geometries? Math is supposed to be clear, and it's supposed to be just one way to do it. How can you have three answers to the question? Euclid says, yes, there's only one line. But if you're on a sphere with Riemann geometry, then you have no lines. But if you have Lobachevsky, then you have infinite lines. So this created a crisis. And so people were saying, well, there are infinite ways to do math. But if there are infinite ways to do math, where's certainty? How do we get that certainty? So here's one, for instance. What is the volume of a four-dimensional hypersphere with a radius r? Anybody who is a graduate student in math should know this. Anybody here done graduate courses in math? Or, like me, do you have access to the internet where you can just ask this question and it'll tell you the answer? Well, first of all, what is a four-dimensional hypersphere? Now, this is a two-dimensional representation of a four-dimensional hypersphere. But there's no reason why you can't figure that out in math. And the answer is half pi squared over r to the fourth. Obviously, you all knew that, right?
Intuitively.
Pardon?
Intuitively.
Yeah, intuitively obvious. That's great.
We knew it all.
That's a great answer. It's intuitively obvious. You can make out, there are infinite ways to do math depending on the preconditions. Okay, so here's the question. If math is more than a mind game, How do we ground it in reality? And that's what Gauss was trying to figure out. How do we show that it's true as well as consistent? See, because a four-dimensional hypersphere, you can show what the radius is, and that's true. I mean, you can show that that's consistent, but is it true? Because there's no such thing. Well, is there or is there not a such thing as a four-dimensional hypersphere? So yes, it's consistent, but is it true? Now, Bertrand Russell said there are four approaches to try to show that math is both true and consistent. This is probably about in the 1890s. Around the turn of the century, people are trying to figure this out. And Bertrand Russell said, well, we can prove that logic is complete and consistent. And so if we can show that mathematics is just a branch, a subset of logic, then we can trust the reliability of logic to prove that mathematics is correct. And then you had Henri Poincaré, who said, he said that the truth of mathematics is based on intuition, that some things are intuitively obvious and are true to everything. It's kind of like in the Declaration of Independence. We hold these truths to be self-evident, and that everybody knows. And he said that's the way you do it. Or there were a group of French mathematicians who published all under the pseudonym Nicolas.
No hats.
What?
No hats.
No hats, yeah. And they're even wearing short pants, so I don't know, yeah. And they said set theory is the way to go. And I'm told that the way to prove that arithmetic is valid starts with set theory. And they published under the name of Nicolas Bourbaki and worked together to argue that set theory was true. And then, now here's the hat. David Hilbert, and he said that the way to do math is to reduce everything to symbolic formulas and then manipulate the formula. They called it formalism. Then David Hilbert, in a mathematical meeting in 1928, challenged the world of mathematics to say, okay, here are the questions that we have to decide at this stage in mathematics. Is mathematics complete? Can we prove everything that we know is true within a mathematical system? Is it consistent? Or will we run into things that are provable but are inconsistent with other things that are provable? And finally, is mathematics decidable? Or are there some questions we just cannot answer? And so he said, as mathematicians, if we are going to ground mathematics and be able to trust it, we need to know the answers to these questions. Well, 2 years later, Carl Gödel answered the question. And here and he published the paper. He read his paper in 30 and then published it, I believe, in 31. And here he is, and this is Life magazine. Now, Life magazine was a major popular culture force in the United States. And that Kurt Gödel would get on the cover of Life magazine shows that a lot of people in America were interested in this. Now, only about 3 people understood it. And when I say about 3, I mean it was actually the correct number was pi, because there were 3 guys who understood it and 1 guy understood 1/7 of it. So there we are. But Gödel, I'm glad you liked that joke. I worked on that one a long time. But here's what Gödel came up with. He called it the Incompleteness theorem. And I'm not going to go into how he proved it, because I don't understand how he proved it. But he did prove it, and mathematicians have universally accepted that he's correct. So, and what he said is that for any f, which is a consistent formal system, there exists a true statement G, which he named after himself, a Gödel statement, which is neither provable nor disprovable in F. So for in any system, there's a true statement which is neither provable nor disprovable. So, and it's a little bit like no mathematical system is consistent, complete, and decidable. And he proved that. So for every F, there is a G of F. So every mathematical system has one statement that can be expressed as this statement is unprovable. Now think about that statement. If it's true, you will never be able to prove it, so you won't know it's true. But if it's false, then you can prove it's true. Does that frustrate you?
Yes.
Yeah. It's similar to what we call the liar's paradox. Now, who's that? Richard Nixon, a noted liar. I could have picked some more recent examples for American presidents, but I didn't want to get into too much trouble, so I just picked somebody who's dead and a long time ago. Nothing I say is true. Now, if that's true, it's false, and if it's false, it's true. So it's one of those statements. It's a self-referential statement that is frustrating. Okay, we call those kind of statements autophagus. Autophagus means they eat themselves. Auto means self, phagus means stomach. Like your esophagus goes into your phagus. And so self-stomach, a self-devouring statement, a self-refuting statement is autophagus. Okay, so here we're back to Kurt Gödel. Now let me show you an example. Let's say that F is a system with odd and even numbers. It has addition and subtraction in it. Okay, now the statement I'm going to make is a Gödel statement. No 3 odd numbers add to 20. Can you prove that? Well, how would you ever try to prove no 3 odd numbers add to 20? Well, the way you would do it is, since the way you get an odd number is you take any number and double it and add 1. So no matter what numbers you take, and odd and even numbers are integers. So whatever integer you take integer x, integer y, integer z, you add, you put them together, you get 20. We'll see if this is true or not. Well, then 2x plus y plus z plus 3 equals 20. So 2x plus y plus z equals 17. So x plus y plus z equals 8.5. But you know that you cannot add 3 integers and get 8.5. So, and how do you know that? Well, you know that by number theory. But that's what you have to import to make that work. But number theory tells you that the set of integers is closed for addition. So QED, there is a G of F. We know the statement is true, but we know there's no way to prove it with odd and even numbers, addition and subtraction. Now, you could add number theory, but no matter what you add, and Gödel showed that no matter how many statements you put into F, there'll always be at least one that is unprovable. Okay, so there will always, if you apply it to computers though, there will always exist a statement G in any program which is obviously true but is unprovable by that program. So let's go back to our original one. If P is a program with odd and even numbers, addition and subtraction, G states no 3 odd numbers add to 20. Because even if you had a Turing machine, an imaginary infinite computer, you could never, it would add 3 odd numbers and see if the result is 20. Well, that could run forever because the set of odd numbers is infinite. And so with a computer with that program, it could never prove, there's a G statement that's not provable, that you know is true. Now, Allan Curry showed that once a mind understands a computer program, the mind can outwit the program. And Allan Curry is, of course, the father of computing. And he showed that once, in the same principle, the mind can understand the program, but the mind can outwit it because it can see a G that the program can't. And so now we're back to this problem. Okay, how many say white should take the rook? How many say white should not take the rook? How many will not raise your hand no matter what I ask you? Okay. Well, white gains a great material advantage by taking the rook. But what does white lose if he takes the rook? Safety, you're right. Because white has an impenetrable pawn barrier. And black can never put the king in check as long as that pawn barrier stands. So white cannot checkmate black, but white can avoid a checkmate and play for a stalemate. It has to make 50 moves without a piece being taken or a check being offered, and it's a stalemate. Now, the reason I put this up here is because in the late 90s, people had developed computer programs which could beat grandmasters. But they gave the computer program this situation, and the computer took the rook. Because the algorithm is to go for material advantage. And so something that it's fairly easy for us as humans to see that we should not do, the computer made the mistake and did it. Now, I'm not saying you can't program a computer to, in this situation, not take the rook. But what I am saying is that unless you program every move, every possible game of computers, you will always find a situation where the human mind will be able to figure out something that the computer can't. John Lucas, who works at Oxford and is a philosopher, and Roger Penrose, who also works at Oxford, worked together to discover the implication of Turing's insight for philosophy of mind. And here's the insight: that the human mind cannot be merely a computer, because it can do things that even an infinite computer cannot do, such as finding G for any P. And since Turing realized the human mind, once it understands a program, can outthink the computer, that the human mind and a computer have to be fundamentally different things. Now, computers now are made out of, used to be made out of wires, and now they're made out of silicon and little pieces of metal. And some people think that the human brain is just a computer made out of meat. But what Lucas has said and what Penrose has helped them figure out is that the human mind is fundamentally, is ontologically different from a computer. And a computer will never be able to think like a mind. The computer can only do things a human mind has imagined. We make algorithms. We imagine what the computer can do. But the human mind can imagine things no other mind has imagined before. And that's what's different. We can think with algorithms, and often we do. That's how we solve a lot of problems in our lives, through algorithms. But we also think in a different way, a way that no computer can think. We have creativity and imagination, and a computer will never be able to think like a mind. So therefore, the human mind cannot be a computer. There's a difference between a computer and a human mind. So, and a computer will never be able to think like a mind. So, here's what Lucas says. Gödel's theorem seems to me to prove that mechanism, by mechanism he means naturalism or materialism. Materialism is false. That is, minds cannot be explained as machines. Now, a lot of people say the human mind, they use an analogy of the computer, and they'll talk about how, we have inputs and outputs and we deal with data, and that sometimes can be a useful analogy. But what Lucas and Penrose are saying is that it is like any analogy, it breaks down, and it is not an identity, it's an analogy. That minds can never be explained as machines. Therefore, the mind cannot be reduced to the brain. Mind and brain are different. Okay, so based on the thought of Gödel, Turing, Lucas, and Penrose, we have seen that there's more to the mind than the material brain. Now, that the aspect of mind that we're talking about is immaterial. So this immaterial aspect of mind exists. And QED, materialism, is false, because materialism says there is nothing but energy, matter, time, and space. And we are showing that there is such a thing as mind. and that mind cannot be explained in terms of energy, matter, time, and space. So therefore, our friend Carl Sagan, who begins his Cosmos series by saying what? His famous words, his famous among materialists is, in the beginning, God created the heavens and the earth. Remember, Carl Sagan goes walking out on the point of land, and the waters, the waves are coming, and the music is playing. And it's the first words in the Cosmos series. You remember what they are? The cosmos is, all there was, all there ever will be. And so since the cosmos, and by cosmos he means energy, matter, time, and space. And since the cosmos is not all there is, or ever was, or ever will be, therefore there is an immaterial aspect to reality. Materialism cannot be true. There is an immaterial aspect to it that we experience in brain.